All right. So one of the neat things about Zoom, there are many things that I'm sure we're like, I don't love about Zoom, but one of the neat things about Zoom is you can actually annotate on my screen, okay? So use that wisely, but I will at some point ask you to sort of interact with the screen a little bit. This is sort of my way of like, yeah, that's a great idea. Come on up to the board and write your answer here, except you don't actually have to get out of your chair, okay? And so part of that will be sort of how we run things. But let's kind of take a look at how notes will typically flow for a class, okay? So today is limits day 1. Now limits is sort of the only unit that I don't really love how the textbook sets it out. So I've sort of chopped it up and reformatted it in a different way, okay? After the limits unit, everything will correspond to a section in the textbook. So if that's like sort of how you operate, just bear with me this first week. It'll all be fine next week, okay? But what I like to do is start off with a what we know and what's new, okay? I think it's really important to root whatever it is that we're learning in something that we already know so that we can then think about what's new, okay? I think the reality is there's no way that you're in Calc 1 and you don't know anything about math, right? It might feel like that sometimes, but I promise you that that's not true. And so the goal here is really to think about not just like, you know, what are we learning today, but thinking about what strengths you bring to this mathematical experience, okay? Because again, I promise you, every single one of you brings some sort of strength, and it's so important for us to recognize that. All right, so we're going to start with this picture here. We've got this graph. It's a weird looking graph, okay? Weird in terms of there's like some things that aren't like the regular graphs that we see. And for example, we might notice that there's like a little open circle here. We might notice that there's an open circle and a dot here. We might notice that like this right here, it almost kind of skips a few values and then starts the function again, okay? But before we panic about like, oh, what a weird graph, let's start off with some things that we know. And so this first part right here, f of -3, can someone either type into the chat or unmute yourself? What does f of -3 ask you to find?
What is the y value at x equals -3?
Perfect. What is the y value at x equals -3? So one thing that we want to note here is that this is an x value, and altogether, this is asking for the y value at x equals -3. And let's go up to our graph. And what would we say that that value is? At x equals
0.
-3, 0. Oh, saw it, Jenny, thank you. So y value at x equals -3 is going to be 0, okay? All right, let's work through these next two. Can someone tell me what f of 0 is? And again, you can unmute or you can type it into the chat. About, yeah, I would say about 0.5. So about 0.5. And if we were to write that as a fraction, because fractions are going to be our best friends here, what would we write that as? Yeah, 1/2, right? We could write this as 1/2. Okay. All right, so f of 3 then, if we look at this graph up here,
2.
I see 2, I see 2, I hear 2. All right, and so when we look at our graph, we want to go to x equals 3, and then we're going to find out where the filled in point is, right? The filled in point is where it's actually defined. And so this corresponds to a y value of 2, right? Now, I'm really glad that no one said 1, but I bet that would be the most popular wrong answer. Why would f of 3 equals 1 be a wrong answer?
That is not the value of x, or that's the value of y at x equals 3. Exactly. The value of y is clearly 2 on the graph.
Yeah, this open circle, exactly. Great sentence there. Open circle means it's not defined there, or it's an open point, or open circle equals undefined. I love it. Okay, so all of those are reasons why we're going to say that that y value is actually 2. Okay, so these are things that we know, right? We've been working with graphs for a while in the XY plane. Yes, that's a great phrase that we could say that there's actually a hole at x equals 3, but we've sort of given it a different value at 2. Okay, so it's almost like someone took this point, picked it up, and put it somewhere else. All right, so some of us have maybe been feeling a little nervous about this idea of limits. And if you are a visual person, like you can look at a graph, then you do know what a limit is, okay? So let's take a look at this first question right here. All right, the limit as x approaches -3 of f of x, all right? Say that one more time. The limit as x approaches -3 of f of x. And so all that's saying is, let's look at our graph. Let's find where x equals -3. Okay, or x equals -3. And I want you to tell me what y value is this function getting close to when x is getting close to -3?
0.
0. Okay. Now, another way to think about that, someone might say, well, let's pick a number close to -3. You might say -2.9. That y value is getting really close to 0. What would be another number, maybe on the other side of -3?
3.1.
All right, and that y value also getting really close to 0. Okay, and so when someone says limit, all they're saying is what's happening when we get really close to the point. They do not care what happens at the actual point. All right, so don't care about what happens actually there. We care about what happens when we get really close. All right, so let's take a look at this second one, the limit as x approaches 0 of f of x. So what might be a good x value to choose to see like what's happening there? What's a number really close to 0? 0.1, okay. And so when I go to 0.1, that might be like right here. I'm gonna go up to that function. What y value is that getting really close to? 0.5, I love it, I love it, okay. And what about if I chose like -0.1? It might be somewhere here, and I go up to that function. What is the y value there?
1/2. We're pretty close.
Yeah, it's getting close to 1/2, okay? So no matter which side I come from, I'm getting close to a y value of 1/2, okay? One last question. The limit as x approaches 3 of f of x. And so let's go back to our graph for a moment. What might be a good x value to see what is close to 3?
2.99.
2.9.
Love it. 2.99. That might be like right here. Tell me what y value that's getting really close to.
1.
Ah, okay. I'm so glad I saw a
2.
2 in there, but it is. If I go up to that function, what's that y value right there? Well, it's closer to 1, right? Okay, let's pick a number on the other side of 3, on the, I don't know, let's say the right-hand side of 3. When we look at the right-hand side of 3, maybe we could say 3.1. It's like right about here. And if I go to the function, what's the y value there? Or what's it getting close to? Yeah, it's also getting close to 1. And so this one, if I come from the left-hand side, I get really close to a y value of 1. If I come from the right-hand side, I get really close to a y value of 1. And so when we want to answer this question, the limit as x approaches 3 of this function, we want to look at our graph and say, what y value is it getting really close to? I don't care what happens actually at the point, but I care what happens as we get close to it. And so for this one, we would say that the limit as x approaches 3 of f of x is 1. All right. This is the first one we've seen where these are not the same. Okay. And so we're going to spend a lot of time looking at some of these interesting points where the y value at that point is actually different from the limit at that point. All right. And so with that, let's go ahead and take a look at this little piece. So what is a limit? You've already completed that intro to limits activity on Desmos. And what I'd like for us to sort of do right now is a little bit of a brain dump, okay? So you can either send this to me via direct message or you can post it out to the general class chat. Either way is absolutely fine. But what I'd like you to think about are, let's talk about this one first. What are some concepts or some ideas about limits? In other words, what is a limit?
It's an output value that a function is approaching for a certain given input.
Okay, so can you say that one more time for me?
Yeah, it's an output value that a function is approaching given a certain input.
Output value that a function approaches given an input value. All right. As a function approaches a certain x value, then what is the y value that it approaches? Love that. So as a function is approaching an x value, what is the y value? All right, a limit is a y value that does not have to be defined. All right, helps us see what a value would be for an undefined solution. Describes the y value that the close x value will approach. Good, good, good. Okay, and so the key phrase here that we really want to think about is approaching. All right, we're getting really close to a certain point. It doesn't matter if we actually get there or not. It's just what happens when we get really close to that. Okay. All right, well, I think brain dumping some concepts is important, but I also think it's important to talk about what questions we have. Okay, and so if you still have some sort of lingering questions or questions you hope we answer, go ahead and dump those into the chat. Again, you are welcome to send them out to everyone. You are welcome to send it directly to me. All versions are fine. I like that. Someone said it's a prediction of a graph as it approaches a point. I love that. All right, so I'll give folks a little bit of time to think about what questions they might have. All right. All right. I mean, obviously, a la Mean Girls, we want to know, when do limits not exist? All right, so when do limits not exist? Application to a piecewise function. Okay. And let's maybe give some thought time, hopefully maybe one more question. I think it's really easy to sort of sit and say, I have so many questions, I don't even know. I just want someone to tell me what's going on. And I will say that that's generally not a super productive strategy. Okay, so we really want to think about like, okay, what do we want to know about? What would be helpful to know? Okay, what does it mean for a limit to be undefined? Okay, so maybe an undefined limit. All right, cool. Well, let's kind of leave this for right now. How do limits fit into the rest of calculus? Like, why do we need them? Excellent. Limits actually are going to help us talk about slope. All right, we're going to spend a lot of time talking about slope and what we need to do in order to find slopes of some sort of weird looking things. And it turns out that limits are really useful in saying, I don't care what happens at the actual point. I care what happens when we get really close to that point. All right. All right. Now let's go ahead and great question. Someone's maybe looking ahead. The limits from negative or positive are different. What do we use the negative or positive for? All right. So let's do one more thing. We'll take a quick break and then we'll come back and actually do some examples. Okay. So this notation, all right, we just sort of read through this earlier and I told you what a lot of things mean, but what I'd like us to do is maybe just like annotate this a little bit more, because I think one of the hardest things about calculus is suddenly we're going to throw a lot of vocabulary in there. We're going to throw a lot of notation in there. We're going to be like, I just want you to know what this means. Okay, so it's important that we support ourselves in this process. So this statement right here really says the following. The limit as x approaches, my goodness. The limit as x approaches, what is x getting close to in this particular definition? A, perfect. The limit as x approaches a of what function? Of f, okay, of f of x is capital L. Okay, so the limit as x approaches a of f of x is L. And so let's think about where all of these different parts come from. All right, so the limit, LIM, that stands for limit. Okay, now the next part we read, however, is the part underneath, and that is the x approaches a. Okay, and we always say of what, like what are we finding the limit of? And there needs to be some sort of function in here. And so sometimes that's an equation, sometimes it's f of x, sometimes it's g of x, but we have some sort of function, some sort of picture that we're looking at. And the number that comes out is L, okay? And so most of the time, when we're looking at this L will be the y value that we're interested in. Okay, so the answer that we get represents a y value. All right. So I think this is a good place to take another stretch break. And when we come back, we'll probably take a look at example 1 and hopefully example 2. Okay, so we'll take a look at some more pictures. We'll actually get to practice some problems. Let's see, it is 8:43 right now. Let's be back at 8:53. Okay, so we'll be back at 8:53. Take a stretch break and I'll see you back here. All right, so before break, we took a look at this notation and we were able to unpack the notation into different pieces. And so learning that when we see something that looks like this, we want to read it as the limit as x approaches a of f of x is L. Okay. And so let's actually try a problem, because I think so often we're like thinking about the concept and it's not until we try a problem that we actually gain some clarity around that. Okay, so let's take a look at this particular graph right here. And so just looking at the graph before we even look at the actual questions, what might be some x values that are interesting for us to think about? All right, so in other words, what are some interesting x values?
X equals 0 seems to be the most interesting.
X equals 0 and x equals 2. Yeah, because at x equals 0, there's some sort of like weird thing happening here. And then at x equals 2, there's also a weird thing happening. Okay, so as unmathematical as that might sound, when we look for things that are weird, that tends to be what we're going to be looking at. Okay, because the non-weird things, they're just so straightforward. They're not really worth, looking at a ton. We want to look more at the more interesting cases. All right. So let's take a look at these questions. All right, so this particular question focuses on the first x value that you folks mentioned, which is 0. We want to know what's happening when we get really close to 0. Okay, now one of the things that you'll notice though is these 3 things in the red circles are slightly different. What's slightly different about them?
The presence of
the
sign.
direction.
Yeah, the plus and minus signs, exactly. We have if I zoom in even more, we have like the tiniest little minus sign here that we don't want to miss. If we look at the second one, we have a tiny little plus. And if we look at the last one, we don't have anything at all, okay? And so when we look at these questions, someone asked this before break, which was a great question. What do the pluses and minuses mean? Okay. And so let's take a look at this. This question, we read it like this. So the y value that the function gets really close to when x approaches 0. And check out what we have here. This left is this minus sign. So when you see the little minus sign, it means, hey, I want you to look at the picture and I want you to look from the left-hand side, okay? And so if we look at our picture here, when we're coming from the left, I would start maybe like somewhere here and I'd keep going and keep going and keep going. Oh, and I don't want to get to 0. I just want to get really close to 0. Okay. What y value is that getting close to? 1. Perfect, Jenny. Nice, nice. Yeah, so when we come from the left-hand side on this picture, we get close to a y value of 1. Okay, so this very intimidating looking question says, find the limit as x approaches 0 from the left, and we'll get a y value of 1. Okay. Now, none of your textbooks make you write out sentences, right? You won't ever see that, but we'll see a lot of this kind of notation. And so what I really want us to do here is make sure we build that understanding of what this notation is asking us for, okay? All right, while I'm highlighting, take a look at question B, type in your guess. What do you think the numerical answer is going to be? Right, so this time we're looking not from the left, but from the right. And if we trace, perfect. I love these guesses. We are indeed getting to 3. Perfect, perfect. So what we want to say is that the y value that the function gets really close to when x approaches 0 from the right is 3. Or if we saw this question right here, we would just say, let's look on the right-hand side. Let's see what the function is getting close to. It turns out it's getting close to a y value of 3. Okay. Now, for B, does it get to 3? Like, does the function actually get to 3?
Yes.
Yeah, it does, right? And that's okay. But what about A? Does the function actually get to 1? No, right? And so that's also okay. It doesn't matter what's happening exactly there. We only care about what's happening from the different sides, okay? All right, so what do you think about this question? If there's no pluses and minuses, what do you think that means?
I think it's from both directions.
You would be correct. We are looking, if there's no plus and minus, it means from both sides, okay? From both sides. And so we can see that right here, both sides, because if we go back, there is no plus and no minus, right? So let's say that you're meeting up with a friend, because we can kind of do that these days. And you're walking this way and you get to where you said you were going to meet your friend. And your friend is walking this way and gets to here. Like, well, this is where we're supposed to be. Do you actually meet? Like, are you in the same place? Nope. You were not in the same place, okay? And so when we're looking for a limit and there's no plus and minus, and what we get from the left is different from what we get from the right, that means that the limit does not exist, okay? Classic line, does not exist, also shorthanded as D and E, not to be confused with a D and R, but a D and E, all right? So it does not exist. And the way we could say that is the y value that the function gets really close to when x approaches 0 from both sides is, they're different from each other. And since they're different, we can say it does not exist, all right? And so that was one of the great questions someone asked earlier. What does it mean for a limit to not exist? This is one really great picture, okay? All right, let's finish this up with part D over here. It says f of 0. And that we know from before. That is saying, find the y value of the function when x is exactly at 0. And we would say, absolutely, folks, that value is 3. Okay. So lots of different symbols, but hopefully with enough words right now to help you move through the symbol, okay? But on your quizzes, you'll notice that those are going to be a lot more stripped down. It'll be a lot more notation. It might not have the sentence piece with it. And so that's where you really want to connect the notation to what it means for yourself, okay? All right, how are we doing with example 1? Feeling good? Feeling terrible? Better than before? Good, good. Okay. All right. See a lot of positive feedback. That's good. Also, folks who are lots of different voices talking. So that is excellent. All right. So now that we kind of know like what a limit is, all right, so like that y value we get really close to when we have an x value we're really getting close to, one question we should be asking ourselves is, great, how do we find them? Okay, so now that we kind of know what it is, how do we find them? And it turns out we're going to be looking at 2 primary methods, okay? The first one is going to be graphically, and we've already done that. All right, so let's work through example 2 before we get to the second way of finding things, which fan favorite is algebra based. All right, so algebra is definitely a big part of calculus, and that tends to be the part where folks are like, I don't like calculus, but it turns out maybe they just don't love the algebra. Okay, so it'll be a good chance for us to review some really important skills algebraically as we move through different kinds of problems. And so let's finish up this graphic one first before we move to the algebraic. Okay. So we saw this graph earlier, and you folks did a great job of predicting. You said 0 was a very weird looking one that we should focus on, and the other one folks said was 2. Okay, 2, the x value of 2 seemed to be a very interesting point. All right, so let's take a look at part A. All right, so we know that this little minus sign means the limit as x approaches 2 from the left is what? All right, so according to this graph, what y value are we getting close to when we get close to an x value of 2? Perfect, Kristen. Nice, Alberto. We've got a 5. Okay. All right. So when we come from the left, we can mark this on the diagram. We're coming this direction, and we see that we get to a y value of 5. All right. What about when we come from the right-hand side with that little plus sign? That's what that's telling us. What y value are we getting close to? Yeah, we go this way. Sure does look like we're getting to the same y value. Nice job. So getting close to 5, and we can say x is approaching 2 from the right gives us a y value of 5. Nice, nice. Okay. All right. What about this one? Part C, where we're looking from both sides. And we know that because there's no plus or minus. So from both sides, it looks like we are getting really close to 5. Right? And one indicator of that is when you look from the left and you look from the right, you get the same number. That number is your limit. Okay. All right. What about f of 2, the y value of the function when x is exactly at 2? What do we think?
Undefined.
Undefined. Love it, love it. Okay, and we can see that. Literally, we can see that because, and someone mentioned this word earlier, that we have a hole in our function. Okay, So this f of 2 we can say is undefined, and that is undefined. All right, how we feeling with the pictures? Pictures seem good? Good, good. Okay. Now, I forgot to mention this earlier, but all the blank notes are on Canvas. And so if you have a tablet or a printer, you can always print those out and it'll be like fill in the blank notes. Okay. If you do not have access to that technology, I think all of the blank notes are up. So if you wanted to find someone with a printer to print those out for you, you know, someone who's got a job that, you know, could just, you could borrow their printer for a bit, that might not be a bad thing to do. Okay. You're certainly welcome to just use the completed notes as well, but I'll just kind of leave that up to you. All right. So the graph part, not so bad. All right, with the algebraic part, what we're going to look at today and tomorrow is a lot of different techniques. And the biggest challenge here is not necessarily that one technique is hard or easy, but the question here is, how do we know when to use which one? Okay, that is a very, very big question for us that we want to make sure we keep in mind. How do we know which strategy to use? Okay, how do we know which strategy to use? Now, that is something that on an exam, say next week's exam, I do like to hear folks explain to me how they knew when to use which strategy. Okay, so it's not just about solving it and getting a number at the end or getting an equation. I might actually ask you to explain that strategy. Like, why did you know to use this method? Why did you know to use that method? Okay, so as I'm talking through these, kind of listen to those things as well. All right, so let's take a look at this first method. Okay, first, I would always, always, always try this first. Okay, so substitution, try this first, right? I don't care how gross the function looks. Like, this isn't so bad, 2x squared minus 3x plus 4, but this one looks kind of gross. X cubed plus 2x squared minus 1 over 5 minus 3x, right? But a good sort of strategy, if you will, is when you're thinking about algebraic methods, try substituting first. I mean, just plug in the number and see what happens, okay? If you plug in a number and you get a number out, what that means is that that point is like somewhere on your graph, okay? So if I plugged in x equals 1 in our previous example, what would you expect the limit to be?
Closer to 4.
Nice, right? Because if we just sort of go up right here, we would expect to get a y value of 4. Very nice, okay? Now, if you plugged in, let's say, this x value, what would you expect the limit to be? Zero. Very, very nice. Okay, what if you plugged in this one? What would you expect to get? Yeah, like negative something. Okay. What if you plugged in 2? What would you expect to get?
No solution.
No solution, exactly. Or we could say undefined. Yeah, we actually wouldn't get 5 out because there's actually a hole. That point got kidnapped. Somebody just took that point, threw it away somewhere. We don't know where it went.
So the limit then is not 5?
Ah, okay. So the limit from both sides is,
Sorry, maybe I misunderstood you.
yeah, but is there a value actually there? No, there you go. Okay. All right. So let's try substitution. So substitution, and I think, Jeremy, you bring up a really good point here. Substitution works for continuous functions. All right, so anything where we can say, this piece, I could draw this without picking up my pen or pencil. I could plug in a value, I would actually get a value out. But when we're looking at points like this, we're going to have to try some other strategies to get that 5 out. But we'll still be able to get 5. We just have to try some different strategies. Okay. All right. So let's do some actual number crunching here, which is weird. We've made it almost all the way through and not really done any number crunching. For example 3, I'm just going to go ahead. I'm going to plug 5 into this function. And so I'll get 2 times 5 squared minus 3 times 5 plus 4. All right, never hurts to review order of operations. What do I do first here?
Exponent.
Exponent, love it, love it. Okay, so I'm not going to do 2 times 5 and then square it. Right? Such an easy mistake. And everybody who makes it is so mad at themselves afterwards. We're going to square it first. So we'll get 2 times 25 minus 3 times 5 is 15 plus 4. And we should end up with, let's see, 50 minus 15 is 35 plus 4 is 39. 39, what does that number represent?
A real output of the function. So a real y value at x equals 5.
Exactly. This 39 is a y value. In fact, it's the y value you get when you get really close to x equals 5. Okay. Now, this function right here, 2x squared minus 3x plus 4. What shape is that? Like if I were to draw this.
A parabola.
Perfect. This is indeed a parabola. Is it facing up or facing down?
Up.
There you go. Parabola, and we could say facing up. Okay. Now, as far as like sketching it out, I wouldn't expect you to sketch this out by hand, but it's kind of handy to know like generally what shape it is. Okay. All right. So let's try this next example. Example 4. We're going to take this gross looking function and the number we're plugging in is -2. -2, perfect. Negatives, you always have to be really careful, right? So -2 cubed plus 2 times -2 squared minus 1 over 5 minus 3 times -2. Okay. And so let's see, -2 cubed. I'll tell you what it's not. It's not -6.
It's -8.
It is -8. I know -6 could happen this early in the morning. I get it. All right, so we've got a -8 here. What about this middle term? What does that simplify to? Positive. Good. So +8 minus 1 and then 5. And I've got a 6 plus or minus? Plus. There you go. Perfect. All right. So -8 plus 8 gives you 0. So we get a -1 over 5 plus 6, which is 11. -1 over 11, just like that 39, is a y value. Okay. And so if you were to graph this rather gross looking function, okay, you would find that you end up with a y value of -1 over 11 when you get really close to x equals -2. Okay. So I know we've got about 7 minutes left. I do want to do example 5 just to kind of get you started on that. And one of the classic algebraic strategies that I think I've never taken a math class and not used factoring. Okay, that is why we are going to have a factoring Desmos activity on Thursday. Okay, and I just want to make sure that it's something that we know how to do, especially some of the more classic cases of factoring. Okay, so if we did not know that this was in factoring, the first thing we should do is plug in 1, right? We would plug in 1 everywhere we see an X. So if I tried substitution, I would get 1 squared minus 1 over 1 minus 1. Let's see, that gives me 0 on the top over, oh crap, 0 on the bottom. Goodness. What's 0 divided by 0?
0.
Okay, so we've got these two answers, right? 0 or well, that's not 0. 0 or undefined. Okay, so when we divide by 0, okay, meaning 0 is in the denominator, we obtain undefined. Okay, so when we divide by 0, okay, that meaning the 0 on the bottom is the problem, means we get undefined. Okay. Now, wouldn't it be nice if we could just write undefined and be on our merry way, except turns out we can figure out what it gets close to. Okay. This right here is exactly what you were talking about earlier, Jeremy. All right, so when I asked what would we get if we plugged in x equals 2, a lot of us said undefined. That other comment though was, but the limit is actually 5. We know from the picture we get to 5 on both sides. This is a case where we probably needed to do some factoring to figure out what y value should be there. Like if we were to plug in that hole, to fill that hole, okay? So here's how we use factoring to get that actual number. Once you get the undefined, you're gonna go back to your original limit as x approaches 1. Now the numerator, I'm going to leave as x minus 1. It's a linear term, not factorable. There's no common factor there. X squared minus 1 though, very classic factoring, right? When we have the a squared minus b squared. All right, perfect. So a squared minus b squared is a plus b times a minus b. All right, so really important shortcut that I find saves so much time. So we'll get x plus 1 and x minus 1. All right, and check this out. We have an x minus 1 on the top. We have an x minus 1 on the bottom. Now, once we've reduced, what do we have left?
X plus 1 over 1.
Good, x plus 1 over 1. And a lot of us might write that as just x plus 1, and that's absolutely fine, okay? Now let's try plugging our number back in. Perfect, nice job, Sophia. We've got a 2, all right. So what does that 2 mean? All right, here's what it means. We have a hole in our graph at x equals 1. Okay, we have a hole in our graph at x equals 1. That's why we got undefined. However, the y value that the function approaches from both sides is 2. Okay, let me get that all on one screen for you. We have a hole in our graph at x equals 1. That's why we got that undefined, okay? However, the y value that the function approaches from both sides of x equals 1 is 2, okay? So this is very similar to that picture we saw in example 2, where they're sort of going to both sides, they're getting close to 5, but we didn't actually get to 5, okay? All right, I think this is a great place to stop. So I'm going to go ahead and stop the recording.